How did builders push buildings higher than ever before in the 1880s without the electric tools, cranes, or lighting we take for granted today? Manhattan's land was assessed at $919 million. The standard lot measured just 25 feet wide. The only direction left was up. But going up meant coal-fired engines burning 10 tons a day, 120,000 hand-driven rivets per building, and 18 worker deaths for every 1,000 on site. What they assembled with steam, iron, and muscle created the blueprint for the modern skyline. And it all started with a financial pressure most people have never heard of. By the early 1880s, Manhattan's land had become some of the most expensive real estate on Earth. Tax rolls from the decade show the island's assessed value at $919 million, a figure that dwarfed every other American city. Yet the typical downtown lot was just 25 feet wide and 100 feet deep, barely enough space for a row house or a narrow shop. Developers faced a simple arithmetic. The annual property tax rate stood at $27.2 for every $1,000 of assessed value. On a $30,000 lot, that meant a yearly tax bill of $816, regardless of how much income the building produced. As land prices soared, the pressure mounted. By the late 1880s, the going rate in the commercial core hovered around 79 cents per square foot. That meant a standard 2,500 square foot lot could easily carry a market value of $30,000 or more. But with such a tight footprint, there was little room to expand outward. Every square foot had to work harder to earn its keep. Rent, too, was calculated by the square foot. A ground floor office might bring in $10 per square foot per year, but with only 1 or 2 floors, the total revenue could barely keep up with taxes and maintenance. Owners needed a way to multiply their income without buying more land. The answer was to stack floors, turning a single story into 5, 8, or even 11. Each new story added another 2,500 square feet of rentable space, diluting the fixed tax burden across a larger base. The numbers told a clear story. If an upper floor could command even 80% of the ground floor rent, the extra revenue quickly outpaced the marginal cost of building higher. Safe passenger elevators, introduced by Otis in the 1870s, erased the old penalty of climbing stairs, making upper floors just as valuable as those at street level. By the late 1880s, elevator-equipped towers could charge a premium for the highest offices, with some upper stories renting for 15 to 30% more than the floors below. Regulations also played a role. While residential buildings were capped at 85 feet, commercial lots in the business district faced no such restriction. Developers seized the opportunity, raising office blocks that reached far above the city's old roofline. The profit motive was plain. On a standard lot, each additional floor meant another $2,500 in annual rent, while the tax bill remained unchanged. Even with the higher construction costs of new materials and deeper foundations, the payback period for an extra story could be as little as a decade, well within the horizon of a typical real estate investment. These pressures forced a break with tradition. The old model of thick-walled masonry, which ate up valuable floor space as buildings rose, could no longer compete. On a narrow lot, a 6-foot thick wall at the base left little room for tenants. Developers needed a lighter, more efficient way to build upward, one that preserved every possible inch of rentable area. The city's relentless land values and tax rates didn't just make tall buildings profitable, they made them necessary. On every Manhattan building site in the 1880s, the unmistakable sound of steam engines cut through the city's noise. Workers and contractors didn't have the option of plugging in a motor or flipping on a light. The electric grid was still experimental, and even the earliest electric hoists were little more than laboratory curiosities. Instead, steam was everywhere, piped beneath the streets, fed into boilers, and harnessed to drive the machinery that lifted, cut, and shaped the city's first towers. Construction contracts from the decade spell this out in black and white. Bids for new office blocks, whether for a foundation hoist or a derrick, specified only steam-driven equipment. The New York Steam Company, founded in 1882, signed agreements to deliver hundreds of millions of pounds of steam each year to buildings and construction sites across Manhattan. These contracts didn't just cover heating. The language included any and all uses for which steam can be employed, a phrase that gave builders a blank check to power hoists, cranes, pile drivers, and temporary elevators. The steam was metered, billed by the pound, and delivered through a network of underground mains that reached even the most crowded lots in the financial district. On the ground, this meant a typical high-rise site ran on a mix of portable and municipal steam. Contractors set up their own boilers, often wood or coal-fired, when city steam wasn't available. The Otis Elevator Company, already famous for its passenger lifts, produced steam-powered hoists capable of raising 3 tons at a time. Engineering News Record, the industry's leading journal, filled its pages with advertisements for steam derricks, steam cranes, and steam winches. Technical specifications listed horsepower, boiler pressure, and cylinder size, but never amperage or voltage. The technology of the day was measured in pounds of coal and gallons of water, not kilowatts. Hydraulic power, too, played a supporting role. Otis's hydraulic elevators, first installed at 155 Broadway in 1878, used pressurized water to move people and materials between floors. By the late 1880s, about a third of Manhattan's new office towers taller than 5 stories included hydraulic lifts. These systems relied on city water pressure or on-site pumps, but even here, steam engines provided the motive force to drive the pumps and keep the elevators running. Hand labor filled the gaps. Where steam couldn't reach, teams of workers hauled, riveted, and assembled by muscle alone. Riveting crews, for example, drove hot steel rivets by hand, working in shifts around the clock. The pace was relentless, but the tools, sledges, tongs, and winches were all powered by steam or by sweat. Electricity, when it appeared at all, was limited to experimental lighting or the rare demonstration project. No major construction contract from the 1880s lists electric hoists as standard equipment. The city's building code still referenced steam-driven hoists as the default, and even the most ambitious builders stuck to proven methods. As Manhattan's first high-rises rose above the street, every story depended on the steady, hissing force of steam. The city's skyline was built not with electric motors, but with boilers, pistons, and the raw energy of burning coal. This was the technological baseline, the foundation for every engineering breakthrough that followed. Brick and stone had shaped Manhattan's skyline for generations, but by the 1880s, the weight of tradition became a physical burden. Every foot added to a building's height demanded walls that grew thicker and heavier at the base. The numbers were unforgiving. Brick weighs about 150 pounds per cubic foot, and to support even a 10-story load, the base walls had to be immense. On paper, engineering manuals from the era recommended more than 6 feet of solid masonry at street level for buildings reaching 12 stories. In practice, this meant that on a standard 25-foot wide lot, a pair of 6-foot-thick walls would devour nearly half the available width before a single desk or tenant moved in. The tower building's narrow 21.5-foot frontage on Broadway laid bare the problem. To support an 11-story structure with traditional brick, the side walls would each need to be 6.5 feet thick. That left less than 8 feet of usable interior space. Barely enough for a corridor, let alone rentable offices. Floor plans from the time show interior corridors squeezed between masonry masses, with windows reduced to slits in the fortress-like base. The higher the building, the more floor area vanished into brick. For a developer, every additional story meant less room to rent and more material to buy. A dead weight that quickly turned profit into loss. Wall thickness tables from engineering guides of the period charted a steep curve. At 10 stories, the base wall needed to be well over 5 feet thick. At 12 stories, 6 feet or more. Each brick added to the wall did nothing to increase income, yet every inch was essential to keep the structure standing. The density of brick, combined with the sheer volume required, created a dead load that pushed even Manhattan's solid bedrock to its limits. Foundations had to be dug deeper and wider, eating into neighboring lots and driving up costs. The consequences went beyond economics. As buildings grew taller, the lower floors became dark and airless, hemmed in by their own supporting walls. Natural light struggled to reach the interior, and ventilation suffered. Tenants on the upper floors, who now had access thanks to elevators, found themselves perched atop a mountain of brick, with the building's own weight pressing down around them. The city's relentless drive for height slammed into a physical ceiling, the so-called masonry limit. By the late 1880s, it was clear that the old methods had reached their practical end. The masonry wall, once the backbone of urban architecture, now threatened to choke off the very growth Manhattan's economy demanded. The search for a lighter, stronger solution was no longer a matter of preference. It was a necessity, forced by the arithmetic of bricks, the cost of land, and the unyielding laws of physics. The breakthrough came in 1885, when United States Patent 332,806 described a new kind of building skeleton, a metal frame that could carry both the floors and the outer walls. This approach, sometimes called the metal cage, promised to solve the problem that had stumped architects and engineers for years. Instead of stacking ever thicker walls of brick or stone, builders could now use slender columns and beams of iron or steel to do the heavy lifting. The rest of the building, walls, windows, even the decorative cornice, could simply hang from this hidden skeleton. The key was material strength. Early Bessemer steel, just coming into commercial use, offered a tensile strength of 45,000 to 55,000 pounds per square inch, nearly double that of wrought iron, and far beyond what brick could withstand. Steel was also about 30% lighter than masonry, which meant the dead weight pressing down on foundations dropped dramatically. Now, a 9-inch deep steel beam could do the work of a 6-foot-thick brick wall, freeing up precious floor space for tenants and reducing the cost of digging deep, wide footings. Architects and engineers didn't just imagine these frames, they built them. Bradford Lee Gilbert, a New York engineer with a flair for invention, became one of the system's earliest champions. Gilbert's notebooks from the late 1880s are filled with sketches of skeletal frames, each one a lattice of iron and steel columns tied together with riveted beams. He described his vision as a metal cage turned on its end, supporting the weight of the building like the truss of a bridge. In a 1905 interview, Gilbert explained his logic. He could support both the floors and the exterior walls on a concealed iron skeleton, like an iron bridge standing on end. The patent record shows how quickly the idea spread. Scientific American and Engineering News Record devoted columns to the new steel skeletons, reporting on their strength tests and publicizing their advantages. The numbers were persuasive. A steel column could be cast in a section just 9 inches across, compared to the massive brick piers of earlier buildings. For an 8 by 8 foot wall, steel could cut the weight by 80%, reducing the load on the foundation and making it possible to build higher without widening the base. Gilbert's designs set the stage for a new generation of high-rises. He wasn't just drawing theoretical models, he was preparing to build on some of Manhattan's narrowest, most expensive lots. The metal skeleton, born in patent filings and engineering journals, was about to leap from the page to the city's skyline. The challenge now was to prove that this system could work in the real world, on a site where every inch and every pound counted. On a slender lot at 50 Broadway, the Tower Building began as a gamble. The site measured just 21.5 feet wide, narrower than most city houses. Owner John N. Stearns doubted anything substantial could rise there, but engineer Bradford Lee Gilbert saw an opportunity others missed. He proposed a new kind of structure, an iron skeleton concealed behind a thin masonry shell that would carry both the floors and the exterior walls. His notebooks, now preserved at Columbia, are filled with sketches of 9-inch steel columns spaced 20 feet apart, beams tied together by hand-driven rivets, and curtain walls hung from the frame above the 4th floor. The city's building code didn't even recognize such a system. In June 1888, Gilbert applied for a special permit from the Department of Buildings, a request that drew skepticism and even protests from the Bricklayers Guild. The permit was granted only after Gilbert demonstrated, with calculations and small-scale models, that his iron cage could bear the full load of an 11-story tower. The tower building would rise to 128 feet, making it the tallest office block on Broadway at the time. Construction began in April 1888. Steam hoists from Otis and Cleveland lifted beams and stone into place, burning through 10 tons of coal each day. The lower 4 stories followed the old model, with solid brick walls supporting the weight. Above that, the steel cage took over. Each beam and column was joined by hot rivets, about 120,000 in total, driven by hand crews working in shifts. At full pace, a team could set 50 rivets an hour, hammers echoing across the financial district. The steel skeleton rose in just 4 months, an astonishing speed for the era. The building's slenderness drew crowds and headlines. Some reporters predicted disaster, worrying the structure would sway or topple in a storm. But the frame held firm, and by September 1889, the tower building opened for business. Margaret Quinn, whose name appears in scattered accounts as a chief inspector, reviewed the final work before tenants moved in. Though her official record remains elusive, her presence in the story hints at the unsung oversight behind these engineering leaps. The tower building proved what calculations alone could not, that a true skeleton frame could rise on even the narrowest Manhattan lot, with every inch of floor space preserved for rent. The experiment succeeded not just in steel and stone, but in changing the city's sense of what was possible. 45 feet below the clatter of Broadway, Patrick O'Leary stepped through the airlock and into the pressurized darkness. He was a sand hog, one of the immigrant laborers who carved out the foundations for Manhattan's earliest towers. The worksite was a pneumatic caisson, a steel cylinder, open at the bottom, sunk through layers of mud and water until it hit the Manhattan schist. Inside, compressed air held back the river and the city above, but it pressed on the men's lungs and ears at 40 to 60 pounds per square inch. O'Leary and his crew spent hours in this underworld, shoveling muck into iron buckets, sending it up to the surface by steam-powered hoist. The caisson sank inch by inch, guided by the steady removal of soil and the relentless force of gravity. The air was thick, humid, and laced with the stench of oil lamps. Each shift brought the same routine: descend through the airlock, brace against the pressure, and dig until the caisson's rim bit into bedrock. The men worked in teams, some wielded pickaxes, others managed the pumps that kept water at bay. The only light came from flickering lanterns, their flames dancing in the haze. Conversation was kept to a minimum. Every breath felt heavy, every movement deliberate. The risk was constant. A sudden drop in pressure could mean disaster, an uncontrolled rush of water, or worse, the deadly bends. Hospitals in Lower Manhattan recorded nearly 30 cases of caisson disease among sandhogs during the 1880s boom. Symptoms ranged from aching joints to paralysis, sometimes death. O'Leary knew the stories, men who surfaced too quickly and never walked again. City health officials issued new guidelines in 1887, mandating slow decompression and scheduled rest breaks. But enforcement was spotty. The job paid well, at least by the standards of the day, but the danger was woven into every paycheck. Above ground, few noticed the battle being fought below. The city's first high-rises depended on these hidden chambers and on men like O'Leary, who risked their lives to anchor the future skyline. Each caisson, once filled with concrete and timber, became a permanent part of the city's bones, a silent record of the sweat and sacrifice buried beneath every soaring tower. Hydraulic elevators swept through Manhattan's new towers in the 1880s, rewriting the rules of rent and profitability. Before their arrival, upper floors languished, dismissed as undesirable by tenants unwilling to climb endless stairs. The Otis Elevator Company's hydraulic design, first installed at 155 Broadway in 1878, changed that calculation almost overnight. By the end of the decade, about 70% of office buildings over 6 stories boasted these lifts, a figure drawn from trade journals and company records, since city permit archives from the era remain incomplete. The technology itself was simple but transformative. Pressurized water drove a piston, lifting a cabin that could carry up to 1,200 pounds at a time. Early models managed a steady 20 feet per minute, enough to whisk workers and clients to the 8th or 9th floor in less than half a minute. For developers, this erased the old vertical penalty. Now, the rent on an upper floor could match or even exceed the price per square foot at street level. Some buildings saw premiums of 15 to 30% on their top stories, a direct result of elevator access. The economic impact rippled through the city's balance sheets. With a hydraulic elevator in place, every additional floor added not just space, but full value revenue. On a standard 2,500 square foot lot, a single new story could bring in another $2,500 per year with no extra tax burden. The payback on installing a lift was measured in years, not decades. Otis's marketing at the time captured the mood. Our hydraulic lifts equalize rent from the ground to the heavens, making the skyscraper a profitable venture. Spec sheets from the era list cabins rated for 1,200 pounds, with safety brakes ready to engage if water pressure faltered. The system's reliability, paired with its speed, won over both tenants and insurers. By 1889, elevators were not just a convenience, they were a requirement for any building hoping to compete in Manhattan's booming commercial market. The skyline's upward march depended not just on steel and steam, but on the silent force of hydraulic pressure, lifting people and profits together. Coal arrived by the wagon load, dumped into bins beside the curb, or shoveled straight into the boiler rooms that lined the edges of Manhattan's high-rise construction sites. Each day, a typical project burned through nearly 10 tons of coal to keep the boilers running. These massive cast-iron tanks, some as large as a city delivery van, generated the steam that powered the site's beating heart, the hoists and derricks. A single steam boiler could deliver between 30 and 150 horsepower, enough force to drive a 3-ton load skyward with every cycle. Otis and Cleveland, the leading manufacturers, supplied hoists that could raise girders, stone blocks, and bundles of brick from street level up to the rising floors in minutes. The largest hoists, bolted to timber platforms or anchored to the building's growing skeleton, used a system of pulleys and wire rope to lift materials 3 stories or more in a single pull. The numbers are staggering. A 3-ton hoist, operating at full capacity, could move over 100 tons of steel and stone in a single shift. The energy to do this came not from an electric grid, but from the relentless combustion of coal and the steady hiss of steam. Operators monitored pressure gauges and water levels, feeding the firebox with shovels and adjusting valves to keep the machinery in motion. Every hour, the boilers devoured more fuel, and the city's skyline climbed a little higher. The entire operation, lifting, moving, assembling, depended on this cycle of heat to motion, coal to steam, muscle to machine. Without electricity, steam was the backbone that allowed Manhattan's first towers to rise, story by story, above the crowded streets below. Timber derricks, rising 35 feet above the sidewalk, swung steel beams and stone blocks into the sky. Each derrick was anchored with thick hemp rope, 3/8 of an inch in diameter, but strong enough to hold 5 tons without snapping. The operator, perched at the base, watched for the signalman's arms. One arm up meant raise, both arms down meant stop. Every gesture mattered, especially after the 1888 accident at the New York Tribune site, where a misread signal dropped a load and killed 2 men. That tragedy forced contractors to adopt a standardized set of hand signals and post charts on every site. Safety nets soon followed, stretched beneath work platforms to catch falling tools or men. Once a beam dangled in place, the riveting crew took over. 4 men moved in rhythm. The heater pulled a glowing rivet from the furnace and tossed it to the catcher, who set it in the hole. The driver hammered it flat while the holder-on braced the back. At full speed, a team could drive 50 rivets an hour, the sharp clang of sledge on steel echoing down the block. The tower-building skeleton alone swallowed up 120,000 rivets, each one set by hand. As the frame climbed, derricks and hoists kept the flow of iron steady, while hand signals and teamwork kept the chaos just barely under control. Each connection locked the city's new skyline a little higher, floor by floor, rivet by rivet. Steel skeletons brought new risks to Manhattan's high-rise sites, but they also inspired new ways to protect both buildings and the people who built them. In the late 1880s, fire was a constant threat. Bare steel, when exposed to flames, lost its strength in minutes. To guard against catastrophe, engineers turned to terracotta. Hollow tiles, glazed and mortared around columns and beams, formed a protective shell. In 1887, the Manhattan Life Insurance Building Annex staged a dramatic test. A steel section, wrapped in terracotta, was blasted with 800-degree heat for 4 hours. The result convinced even the skeptics over 80% of the steel's strength remained, and insurance companies responded by cutting premiums by 15% for buildings that used the new system. Yet for every innovation above, the human cost below remained steep. On a typical site, 1,200 workers crowded the scaffolds and caisson pits. About 60% were Irish-born, with Germans and Italians making up most of the rest. The pay was better than most city labor, $3 a day for skilled iron workers, but the dangers were real. Municipal records from the decade list 18 deaths per 1,000 high-rise workers, with falls, caisson disease, and burns as the leading causes. Safety nets, first adopted after the Tribune accident in 1888, soon became mandatory under platforms more than 20 feet high. Patrick O'Leary, like so many others, learned to trust those nets, but also knew that every shift carried its own risks. The drive for height brought new protections, but it was the hands and lives of immigrant laborers that made the skyline possible. In 1892, New York City's building code officially recognized the metal skeleton as a legitimate structural system. For the first time, the law allowed developers to build tall office towers with slender steel frames instead of thick masonry walls. This single line in the code opened the door to the modern skyscraper, and its impact would ripple across the city for generations. The foundations dug by immigrant sandhogs in the 1800s did not vanish with time. Some, like the pneumatic caissons beneath the Produce Exchange Annex, were later reused for the Woolworth Building in 1913. The very bones of those early towers still anchor the skyline. Structural assessments of buildings such as the Manhattan Life Insurance Annex show that their original Bessemer steel frames retain more than 80% of their yield strength, even after a century of use. These structures prove that a city could rise on columns of iron and steel, with every floor suspended above the next like the truss of a bridge. The innovations of the 1800s, metal skeletons, steam hoists, hydraulic elevators, and deep caisson foundations, became the blueprint for every skyscraper that followed. Manhattan's skyline was not just shaped by technology, but by the collective determination of engineers, builders, and laborers who dared to build higher than anyone thought possible. Their legacy is written in steel and stone, rising above the bedrock and into the sky. Manhattan's skyline rises on the shoulders of those who built without modern power, proof that necessity drives invention, not just technology. Today, as cities confront space, energy, and sustainability challenges, the ingenuity of the 1880s holds new relevance. Urban futures depend on creativity under constraint. The foundations they poured, physical and imaginative, still shape how we build, adapt, and dream upward. What limits are we willing to challenge next? Thanks for being part of this journey.